Hi everyone, in this video we're going to be talking about solving inequalities involving quadratic functions. And so we have our quadratic function. Notice that's this form right here, ax squared plus bx plus c. It's going to be greater than 0 or less than 0. And the way that we solve these inequalities involving the quadratic functions is we determine where the function is above the x-axis if we have our inequality is greater than 0, or where our function is below the x-axis if our inequality is less than 0. Okay? And then if the inequality isn't strict, then we include the x-intercepts. And what that means is not strict is when we can equal the endpoints, so we can equal our x-intercepts. So if you see the equal bars, then you can include your x-intercepts. So let's jump right into our first example. So notice we have our quadratic function right here, and it's an inequality less than or equal to 0. We want to solve for what x values would make this true. And so the way that we're going to do this is we're going to actually graph this quadratic function. So notice what we just did. It's very subtle, but we took our function and we set it equal to f of x. So we're ignoring this less than or equal to 0 for just a little while we focus on graphing this function. Okay, so using some ideas we've learned in the past to graph a quadratic function. Let's first find the y-intercept. So remember that just means you plug in 0 for x. So if you do that, you're going to get negative 15. And your x-intercepts, remember how that goes. You set your function equal to 0 and you solve. And a lot of times this will factor. If not, remember you can always use your quadratic formula to solve if this doesn't factor. And so this one does factor. And so we have x minus 5 times x plus 3. And so x minus 5 equals 0, or x plus 3 is 0. And so we have two x-intercepts at negative 3 and 5, and then our one y-intercept at negative 15. Okay, so the vertex, this is also something we've learned previously, that we have a vertex formula, and for your vertex, which is your lowest or highest point of your parabola for your quadratic function, the x value is found by taking negative b over 2a, and then the y value is found by plugging that number into your function. So you have an x value and a y value for your coordinate of your vertex. So the x value, b for us was 2, a was 1, and so when you plug that in to negative b over 2a, and you get 1. And just real quick reminder, if you're thinking about where I got a, b, and c from, that is just from your, in general, quadratic function. A is the coefficient on x squared, b is the coefficient on x, and then c is your constant. Alright, so we got 1, and then if you plug 1 back into your function, so let's just work that out really quick. F of 1, that would be 1 squared minus 2 times 1 minus 15. And so that's 1 minus 2 minus 15. And that's where we get this negative 16 from. So that's going to be our vertex. So we have our two x-intercepts that we found at negative 3 and at 5. We have our one y-intercept right here at negative 15. And then we just found our vertex down here at 1 comma negative 16. Now, we have to go back and say, wait, this was an inequality. So let's answer the question. So originally, we were asked, when is x squared minus 2x minus 15 less than 0? And so it's less than 0, because that's our function, that's our parabola. It's less than 0 anywhere underneath the x-axis. And so it's underneath the x-axis, or less than 0, between here, which is negative 3, and between here, which is 5. And so that's how we answer it. We say that our answers for x are between negative 3 and 5. And so our final answer, we can answer it two ways. We can say the solution set, the set of all x's, such that x is greater than or equal to -3 or less than or equal to 5, or in interval notation from -3 to 5. And our inequality originally had an equal bar on it. I think I left that off on the last slide, but it had an equal bar, so it was less than or equal to 0. And that's why we're using the brackets, because we can include these endpoints. We can include where it touches the x-axis where it's 0. And so if we pick any x number in between -3 and 5, and we plug it back into our function, it will satisfy this original inequality. And you can check if you're not sure if you did this correct. Pick any number between -3 and 5, and you should get that it satisfies this. For example, we could just do this real quick. We could pick 0, plug that in, plug in 0 here, plug in 0 here, and we would get -15, and that is definitely less than or equal to 0. And so this is what it looks like on a number line, the answer. From -3, anything in between there, all the way until 5 would work. We could plug that in for x. Alright, let's go ahead and try another one. This time we have x squared is less than x plus 6. So we're going to solve this inequality, and I'm actually going to show you 2 ways to do this. So the first one, option 1, is going to be really similar to what we just did. And so we're going to move all of our terms to one side of this inequality so that it looks like a quadratic function on one side and 0 on the other side. And so if you just subtract x on both sides and subtract 6 on both sides, then you get x squared minus x minus 6 is less than 0. And so that's going to be equivalent to our original, just looks different, and then we can solve that one. So we want to know when is this less than 0, so we're going to focus on just graphing the original or regular quadratic function, and then afterwards look for when this is less than 0. Okay, so real quick, we're going to find our y-intercept, plug in 0, you're going to get -6. X-intercepts, set this equal to 0. So again, you can use your quadratic formula here or factor. This one does factor. So x minus 3 times x plus 2 is the same thing what we just had. And so if we solve, we get x is 3 and x is -2. Okay, so those are our intercepts. We have a y-intercept at -6 and then 2 x-intercepts at -2 and 3. And then using our vertex formula, plug in 1 for b and also 1 for a, and we get 1/2. So that's our x coordinate. And then if you plug 1/2 or 0.5 back into your function, you're going to get -6.25. So real quick, that's from taking either 0.5 or 1/2 and plugging it back into -x minus 6. So if you simplify that, you're going to get -6.25. Alright, so if we graph, we have our x-intercept at -2 and 3. We have our y-intercept right here at -6. And then our vertex is just right a little lower than that, 1/2, comma, -6.25. And remember, when we rearranged our inequality, we wanted the function to be less than 0. And so less than 0, this is really similar to the last one, is down here between -2 and 3. And so that's going to be our answer for this one. We want all x's such that x is greater than -2 but less than 3, or in interval notation, any numbers between -2 and 3. Alright, so I am going to show you another way to do this one. It's kind of interesting. Because of the way this was originally set up, this looked like x squared is less than x plus 6. So option 2 lets us work on each of these sides of this inequality as 2 separate functions. So we can say that the left side is f of x and the right side we'll call g of x. And so we're just looking for when f of x is less than g of x. And so we'll graph each of these. Okay, so remember how this one looks. This is your standard parabola centered at the origin. So 0, 0, 1, 1, 2, 4, and then you mirror those points. Okay, so that's this one, f of x. And then this g of x, that's just a line. So that's the line x plus 6. So your slope is 1 over 1, an invisible slope here. So real quick, that is y equals 1x plus 6. So your y-intercept is 6 right here, and your slope is 1. So you would rise 1 and run 1. Rise 1 and run 1. Okay, so that's how you can graph both of those functions. So we graphed the two functions, so let me label, this one's g, this one's f. And then we consider that we want to know when one was less than the other one, but real quick before we do that, let's figure out these intersecting points. So we have to solve for when they're equal to find those 2 points where we intersect. So even though this is the inequality we're trying to solve, for just the time being, we are setting this equal to each other because we need to figure out when our two graphs intersect. So if we set that equal, then after that we do have to solve this quadratic equation. Notice this is a quadratic equation, not an inequality at the moment. And so this is similar to option 1 for finding the x-intercepts. And then we solve our equation. We get x is 3 and x is negative 2. And so the graphs intersect at negative 2, 4 and 3, 9. Okay, really fast, where the 4 and the 9 came from. Those came from plugging in the numbers back into the functions. So either function you want, if you plug in negative 2, so you could say f of negative 2, you're going to square that and get 4. Or you can say g of negative 2, you're going to add 6 to that and you'll get 4. Same thing with 3. If you plug in 3 into either function, you're going to get 9. Okay, so those where those points came from. So now we have everything we need to finish this. We have where these two graphs meet at negative 2, 4 here and 3, 9 here. And we wanted to know when is f of x less than g of x, or when x squared is less than x plus 6. And so reminder, this was x plus 6, this one was x squared. X squared is less than x plus 6 over here. So pretty much when is the blue underneath the red because it's less than. And so that is between here, which is at negative 2, and here, which is at 3. So we want all the numbers between negative 2 and 3, and that's going to be our answer, our solution set. We don't include the negative 2 and 3, we don't have brackets because this was strictly less than, this inequality symbol. And that is going to satisfy our inequality. And if you want to check, pick any number in between negative 2 and 3 and you can verify that this is going to work. So let's go ahead and just pick 0. So if I plug in 0, 0 squared for x squared, is this less than 0 plus 6 for x plus 6? 0 is less than 6. Yes, that works. So we are correct on that one. Okay, well, just one more here. So solve this inequality. X squared plus x plus 2 is greater than 2. So this function has a y-intercept at 2 if you plug in 0. So remember, just f of 0, plug that in, you're going to get 2. Then this graph actually has no x-intercepts. So remember this from when we learned about quadratic functions. If you look at your quadratic formula, but really if you just focus on the part of the square root, that's called the discriminant. And if you just focus on this part and you plug in a, b, and c, for us a is 1, b is 1, and c is 2, that's going to look like 1 squared minus 4 times 1 times 2, which is going to be 1 minus 8, which is negative. And anytime you're negative for the discriminant, this is going to be something negative inside of a square root, which is imaginary. So we don't actually have x-intercepts. And so you could solve the whole quadratic function or formula if you wanted to, but you could stop right there because at that moment you're going to have an imaginary number. And so we don't have x-intercepts on this graph. Then we use our vertex formula, so negative b over 2a. Just plug in a as 1 and b as also 1, and simplify. You'll get negative 1/2, and then plug that number back into your function, and that's where 7/4 comes from. So there's our vertex. And then putting that together, take a look at what we have. We have our vertex, we have our single y-intercept right here, but no x-intercepts. And so our inequality greater than 0 is always true. This function, any value for x that you pick, this is always above the x-axis. This is always greater than 0. And so no choice for x would cause a problem. And so the answer on this one is all real numbers, negative infinity to infinity. Okay, so that is it for this one. Thank you for watching.